Hello, this is an educational video for neuroscientists. It's about membrane equations, the Hodgkin and Huxley formalism, and ionic currents in neurons. My name is Wolfgang Stein and I run the Crab Lab at Illinois State University. I'm going to assume that you know about neurons, membrane potentials, and action potential generation. In my last video I explained how ionic currents in neurons can be calculated using the current equation. Here's the equation. The ionic current is the maximum conductance of the ion channel times the activation variable M times the inactivation variable H times the driving force V minus E. M and H range from 0 to 1 and represent the open probabilities of the gates of an ion channel. For example, the fast sodium channel has two gates, an activation gate called M and an inactivation gate called H. Both have to open to pass ionic current through the channel. In other words, M and H must be non-zero. In this video, I will explain why we need a differential equation to calculate the current and how we do this. The problem of this equation is that the activation and inactivation variables are functions of the membrane voltage. Yet, the membrane voltage is altered by the ionic current. Hodgkin and Huxley addressed this chicken and egg problem by making a very simple assumption. There are two states that a single gate can be in, open or closed. The open probability is depicted here with M and the closed probability with 1 minus M. For example, if the open probability is 0.5, then the probability to be closed is 1 minus 0.5 or 0.5. Thus, M corresponds to the percentage of open gates and 1 minus M to the percentage of closed gates. A gate changes from open to closed with the rate alpha and from closed to open with the rate beta. Knowing this, we can calculate the change of M over time by writing the M over dt equals alpha times 1 minus M minus beta times M. This is the same as alpha minus alpha plus beta times M. Obviously, since now the change of M over time is a function of M itself, this equation cannot be solved directly. However, we do know one state in which we know the size of the change in M. In steady state, when nothing changes, the change of M over time is 0. This happens when we stay at the same membrane potential for a very long time, theoretically infinitively long. In this case, M becomes M infinite. Now let me rewrite the equation. So 0 equals alpha minus alpha plus beta times M infinite. Now we can solve for M infinite and get M infinite equals alpha divided by alpha plus beta. This is great, since we now can calculate the open probability of this ion channel gate in steady state, when a particular membrane potential has been kept for a very long time. We just need to know what alpha and beta are. As shown above, they are the rates with which the gate switches from open to closed and vice versa. They are both functions of voltage. Hodgkin and Huxley empirically determined that the relation between M infinite and voltage has a sigmoidal shape. Here's the mathematical description of this sigmoidal curve. M infinite equals 1 over 1 plus e to the power of v minus v 1/2 divided by k. V is the voltage, and there are only two additional parameters that describe this curve, v 1/2 and k. This is the shape that we get when we plot this function. We see the sigmoidal change of M infinite over the membrane voltage. V 1/2 is also called the half maximal potential. At this membrane potential, M infinite becomes 0.5. In other words, at this membrane potential, 50% of all M gates are open. We can also see this in the equation. When the half maximum potential equals V, this term becomes 0 and e to the power of 0 is 1, making the denominator 2 and the whole term 0.5. K is the slope of the curve at that point. That is all we need to know to describe the steady state open probability of the M gate. Now back to our original question. How can we determine the change of M over time when it's not in steady state? Here's the equation from above again. Let me do a mathematical trick here and multiply both sides by 1 divided by alpha plus beta. we get 1 divided by alpha plus beta times dm over dt equals alpha divided by alpha plus beta minus m. This doesn't seem much of an improvement, but we have also shown previously that m infinite is alpha divided by alpha plus beta, which is exactly what we have on the right side of this equation. So now we can write 1 divided by alpha plus beta times dm over dt equals m infinite minus m. Or we can change this to dm over dt equals m infinite minus m divided by tau. Tau is defined as 1 divided by alpha plus beta. We call tau the time constant because it describes how quickly m changes from one state to another. The advantage of this way of writing the dm over dt is that it is a differential equation of the generic form dx over dt equals b minus a times x. And there are mathematical ways to approximate this equation using an exponential Euler or a Runge-Kutta method. I will not get into the details of how to do this, but it involves many small step iterations with high time resolution. One last word about tau. The time constant is also a function of the membrane voltage. In other words, the membrane potential determines how quickly the state of a gate can change. It is a sigmoidal function for many ion channels of the form tau of V equals tau low plus tau high minus tau low divided by 1 plus e to the power of negative V minus the half maximum potential divided by S. And again, the sigmoidal shape can be seen here. The half maximum potential is the membrane potential at which the time constant is in the middle between its lowest value tau low and its highest value tau high. S is the slope at this membrane potential. Remember how we started at the beginning of this video. We wrote the current equation. Now we can populate it with the activation variable m as a function of V. We can do the analog with the inactivation variable h, and then the ionic current can be calculated for a given time point. You may have noticed that I added two exponents, p and q here. Those were empirically added by Hodgkin and Huxley to better describe the behavior of the ion channel gates. For the fast sodium channel, they found that p equals 3 and q equals 1, which best fits the experimental results. At the time, Hodgkin and Huxley did not know about the structure of the sodium channel. We know now that the exponents correspond to the number of conformational changes a single gate has to go through to change its state. Finally, let me say that P and Q affect the time domain of the gate opening and of course of the gate closing, but not the voltage domain. With these equations, most ionic currents in neurons can be adequately described and modeled in computer simulation.